Welcome to this video on OSPF weight setting problem and performance comparison of OSPF versus RIP. In this video, we'll dive into the OSPF routing protocol, exploring its fundamentals and operation. We'll also compare it with the RIP routing protocol to understand how both function in a network environment. Routing is the task of finding a path from a sender to a desired destination. Routing is complex in large networks because of the many potential intermediate destinations a packet might traverse before reaching its destination. A routing table instructs the router how to forward packets. The routing protocols employ different operations to analyze different incoming update messages to produce their routing tables. Given a packet with an IP destination address in its header, the router performs a routing table lookup, which returns the IP address of the packet's next hop. OSPF, or Open Shortest Path First, is a routing protocol used in IP networks. OSPF requires routers to exchange routing information with all other routers in the network. Complete network topology knowledge, that is the arrangement of all routers and links in the network, is required. Because each router knows the complete topology, each router can compute all needed shortest paths. OSPF calculates routes as follows. Each link is assigned a dimensionless metric called cost or weight. The cost of a link is an integer value. The cost of a path in the directed graph is the sum of the link costs. Using Dijkstra's shortest path algorithm, OSPF mandates that each router computes a tree of shortest paths with itself as the root. The link weights are assigned by the network operator. The lower the weight, the greater the chance that traffic will get routed on that link. One approach is to assign the OSPF metric as the inverse of the link bandwidth. On the other hand, if each link cost is set to 1, the cost of a path is equal to the number of links or hops in the path. Let's understand the OSPF weight setting problem using a built-in experiment in NetSim. Open NetSim and click on the Experiments tab in the left panel. Navigate to Internetworks, Routing, and Switching, then expand the first experiment, the OSPF weight setting problem and the performance comparison of OSPF versus RIP. Click on the OSPF weight setting problem. Then select the experiment, output cost as 1. This will load the experiment into NetSim. Once the experiment is loaded, a network scenario is displayed in the NetSim GUI, consisting of 7 wired nodes and 7 routers. Click on any router and navigate to Router Properties on the right panel. Under the application layer, the routing protocol is set to OSPF, retaining all its associated properties at default values. The routing protocol parameter is global, meaning that any modification in one router will automatically apply to all routers in the network. As a result, OSPF is now configured across all routers in the scenario. Now, scroll down to Interfaces and expand all the interface settings. In the VAN outgoing interfaces of all routers, you will see that the output cost is set to 1. The output cost parameter, found under the VAN interface in the application layer, represents the cost of transmitting a data packet through that interface and is measured using the link state metric. Now, click on link ID 15, navigate to its properties on the right panel, and expand the settings. The maximum uplink and downlink speed is configured as 100 megabits per second. The uplink and downlink BER is set to 0, and the uplink and downlink propagation delay is 0 microseconds. Next, click on link ID 12. Go to its properties on the right panel and observe that the maximum uplink and downlink speed is configured as 1000 megabits per second, while the rest of the properties remain at their default values. To configure an application between 2 nodes, go to the Set Traffic tab at the top, select the desired application, and establish a connection between the source and destination nodes. In this experiment, 4 CBR applications have been configured from Q1, R1, S1, and W1 to T1. Click on any application and navigate to its properties in the right panel. Expand the settings and under Application, go to Transport Protocol, where the Transport Protocol is set to UDP. Further, scroll down to the mean generation rate, which is set to 50 megabits per second. To achieve this, the packet size is configured as 1460 bytes, with an interarrival time of 233.6 microseconds. Additionally, the start time of the application is set to 10 seconds. This time is typically chosen to be greater than the duration required for OSPF convergence, that is, the exchange of OSPF information between all routers, and it increases as the network size grows. Now, go to the Configure Reports tab. As you can see, Packet Trace is already enabled. Using Packet Trace, we can analyze the route chosen by packets to reach their destination based on the OSPF routing protocol. Next, run the simulation for 20 seconds. Once the simulation is complete, the result dashboard will appear. Note the throughput of each application, then navigate to Traces and open the packet trace. Wait for the Excel sheet to load. Now, filter the packet type to CBR, then further filter control packet type or app name to the respective traffic flow. In this case, we filtered control packet type or app name as traffic R1T1. From the packet trace, you can observe that the source ID is node 10 and the destination ID is node 13, corresponding to R1 and T1, respectively. To analyze the packet flow, we consider packet ID equals 1, and for this packet, the flow follows this path: node 10 to router 5, router 5 to router 2, router 2 to router 6, and router 6 to node 13. For this example, with OSPF output cost set as 1, the cost or weight of each link is 1. The shortest path from Q1 to T1 is Q1 to Q, then to U, then to T, and finally to T1. The total cost is 2. The shortest path from R1 to T1 is R1 to R, then to U, then to T, and finally to T1. The total cost is 2. The shortest path from S1 to T1 is S1 to S, then to U, then to T, and finally to T1. The total cost is 2. The shortest path from W1 to T1 is W1 to W, then to T, and finally to T1. The total cost is 1. Now, let's analyze the throughput in case 1, where the output cost is set to 1. The throughput for applications Q1 to T1, R1 to T1, and S1 to T1 is 32.71 megabits per second, while the throughput for W1 to T1 is 50 megabits per second. Despite the traffic generation rate being 50 megabits per second per application, the achieved throughput for Q1, R1, and S1 to T1 is only 32.71 megabits per second, indicating significant underperformance relative to the demand. This occurs because the link from U to T has a 100 megabits per second capacity, but the total input rate is 150 megabits per second. As a result, the available bandwidth is equally split among the 3 flows, each receiving approximately 33.33 megabits per second. To overcome this issue, the link weight configuration is optimized. Now, let's move to case 2 of this experiment, adjusting OSPF link weights to improve network performance. In this experiment, we will understand how the weights are configured and how this optimization enhances network performance. Let's take the same scenario and configure the properties for case 2. Go to Router R's Properties, navigate to the application layer, then to OSPF, and finally to Interface 1. Here, you will see that the output cost is configured as 3. Now, run the simulation for 20 seconds. After the simulation completes, the result dashboard will appear. Note the throughput of each application, then navigate to Traces and open the packet trace. Wait for the Excel sheet to load. Now, filter the packet type to CBR and further filter control packet type or app name to traffic_R1_T1. Observe how the packet flow has changed due to the modification in the output cost. Let's understand the packet flow when the output cost of router R is changed to 3. Increasing the output cost on the link from R to U to 3 leads to different shortest paths being chosen by OSPF for some nodes compared to case 1. For example, in case 2, node R1 selects an alternative route through nodes V and W to reach T1 due to the higher cost on the direct RT link. This weight adjustment helps balance the load across links by redistributing traffic, effectively reducing congestion on the link from U to T. The shortest path from Q1 to T1 is Q1 to Q, then to U, then to T, and finally to T1. The total cost is 2. The shortest path from R1 to T1 is R1 to W, then to W, then to T, and finally to T1. The total cost is 3. The shortest path from S1 to T1 is S1 to S, then to U, then to T, and finally to T1. The total cost is 2. The shortest path from W1 to T1 is W1 to W, then to T, and finally to T1. The total cost is 1. Now, let's analyze the throughput in this case, where the output cost is set to 3. By optimizing the OSPF weight configurations, traffic from R is now routed through V and W to reach T1. This redistribution reduces congestion on the link from U to T link, which now carries only 2 flows totaling 100 megabits per second, while the link from W to T carries the other 2 flows, also totaling 100 megabits per second. As a result, the throughput for applications Q1 to T1, R1 to T1, S1 to T1, and W1 to T1 improves to 49.06 megabits per second. As we have seen the throughput variation in both cases, first with the output cost set to 1, and then with the output cost set to 3, case 2 effectively distributes the load, ensuring that the network can handle the traffic demand efficiently. This demonstrates how adjusting OSPF link weights can significantly enhance network performance by optimizing traffic distribution and minimizing congestion. Let's move on to Part B of this experiment: performance comparison of OSPF versus RIP. Routing Information Protocol, RIP, is a routing protocol based on the Bellman-Ford, or distance vector, algorithm, which has been used in computer network routing since the early days of the ARPANET. In distance vector algorithms, each router maintains a routing table that lists the best route to every destination in the network. To determine the best route, a measurement called the metric is used. RIP's metric is hop count, meaning it simply counts the number of routers a message must pass through. The total metric for a route is determined by summing up the costs of individual hops. The best route is the one with the fewest hops, making RIP a minimum hop routing algorithm. Advantages of minimum hop routing: it allows traffic to reach its destination while consuming the least total bandwidth in the network. If a demand requires D amount of bandwidth, the total bandwidth used is D times H, where H is the number of hops on the route. If H-min represents the minimum number of hops for the shortest path, then H-min less than or equal to H, meaning minimum hop routing optimizes resource usage. Limitations. However, bandwidth consumption is not the only factor in determining an efficient routing strategy. Let's take an example to compare the performance of RIP and OSPF to demonstrate the differences between these two protocols. In this example, we have 11 routers connected viaduct wired links, shown in blue, with each link having a bandwidth of 100 megabits per second. Suppose router W is sending 50 megabits per second of traffic to Z, and router U is sending 50 megabits per second of traffic to V. Now, there is an additional traffic demand of 50 megabits per second between routers X and Y. Instead of routing the traffic through C, D, E, RIP follows the minimum hop count rule and routes the traffic through link from A to B, which is already congested. This issue can be addressed in OSPF by configuring the appropriate link weights, as discussed in Part A. Let's understand the same scenario using a built-in experiment in NetSim. Open NetSim and click on the Experiments tab in the left panel. Navigate to Internetworks, Routing, and Switching, then expand the first experiment, the OSPF weight setting problem and the performance comparison of OSPF versus RIP. Click on Performance Comparison of OSPF versus RIP, then select the experiment RIP. This will load the experiment into the NetSim GUI, which consists of 6 wired nodes and 11 routers. Additionally, 3 CBR applications have been configured: W1 to Z1, U1 to V1, and X1 to Y1. Now, click on any router and navigate to its properties in the right panel. Go to the application layer, then to RIP. The selected routing protocol is RIP, with its associated properties retaining their default values. Next, click on link ID 4 and go to its properties on the right panel. Expand the section to view its details. The maximum uplink and downlink speed is 100 megabits per second. The uplink and downlink BER is 0, and the uplink and downlink propagation delay is 0 microseconds. To configure the application between a source and a destination, go to the Set Traffic tab at the top and select the desired application. In this case, 3 CBR applications have been configured. Now, click on any application, navigate to its properties on the right panel, and expand the section. Scroll down to Transport Protocol, which is set to UDP. Next, scroll down to Mean Generation Rate, which is set to 50 megabits per second. To achieve this, the packet size is 1,460 bytes, and the inter-arrival time is 233.6 microseconds. Additionally, the start time parameter is set to 10 seconds during configuration. This value is typically chosen to be greater than the time required for route convergence and increases as the network size grows. Next, go to the Configure Reports tab. As you can see, Packet Trace is already enabled. Now, run the simulation for 20 seconds. Once the simulation completes, the result dashboard will appear. Note the throughput, then navigate to Traces on the left panel and open Packet Trace. Wait for the Excel sheet to load. Filter the packet type to CBR. Filter Control Packet Type, or App Name, to Traffic X1Y1. Filter the Packet ID column to 1. The packet flow starts from the source, which is node 14. It then moves to router 3, then to router 4, followed by router 5, then to router 8, and finally reaches the destination, which is node 17. Let's understand the performance of the RIP protocol. The observed throughput for all 3 applications, W1 to Z1, U1 to V1, and X1 to Y1, is 32.70 megabits per second. However, the generation rate for each application was 50 megabits per second. This discrepancy occurs because the total traffic demand was 150 megabits per second, while the link capacity was only 100 megabits per second. As a result, the available bandwidth was evenly split among the 3 flows, with each flow receiving approximately 33.33 megabits per second. Now, using Packet Trace, we can observe the shortest paths. From W1 to Z1, the packet moves from W1 to W, passes through A and B, reaches Z, and finally arrives at Z1 with a hop count of 3. From U1 to V1, it starts at U1, goes through U, A, and B, reaches V, and finally arrives at V1 with a hop count of 3. From X1 to Y1, the packet travels from X1 to X, moves through A and B, reaches Y, and finally arrives at Y1 with a hop count of 3. The shortest paths are determined based on hop count, as RIP is the active routing protocol. With minimum hop routing, all traffic follows the 3-hop path X to A to B to Y. Since the link from A to B becomes fully utilized, the network becomes partitioned for any future demands. A better approach would have been to distribute the traffic over a 4-hop path, even though it consumes more resources. However, due to RIP's hop count limitation, these alternative paths are not utilized, restricting network efficiency. To overcome this issue and enhance network efficiency, we will use OSPF as the routing protocol, which allows wait setting. Now, let's understand this with the help of NetSim. Consider the same network and click on any router. Go to its properties on the right panel, navigate to the application layer, and select OSPF as the routing protocol. Scroll down to Interfaces, and in all the routers' WAN outgoing interfaces, set the output cost to 1. Next, click on Router X, go to its properties on the right, navigate to the application layer, then to OSPF. Scroll down to Interfaces, and in the WAN Interfaces, output cost and set it to 4. Now, run the simulation for 20 seconds. Once the simulation completes, the result dashboard will appear. Note the throughput of each application, then navigate to the traces on the left and open the packet trace. Wait for the Excel sheet to load. Filter the packet type to CBR, then further filter the control packet type or app name to traffic X1Y1. Next, filter the packet ID to 1. Now, observe the packet flow in the packet trace for the OSPF case. The packet travels as follows. From node 14, which is X1, to router 3. From router 3 to router 9, which is C. From router 9 to router 10. From router 10 to router 11. From router 11 to router 8. Finally, from router 8 to node 17, which is Y1. This shows that OSPF has selected a different route than RIP, highlighting its ability to choose paths dynamically based on link cost. Now, we will analyze the throughput performance of OSPF in this scenario. Here, the traffic generation rate at each node was approximately 50 megabits per second, and all 3 flows successfully meet their expected throughput demand of 50 megabits per second. This is because the traffic from X1 to Y1 is now routed through the CDE link instead of the AB link. Since the traffic from X1 to Y1 is now using the CDE link, the total traffic flow on the AB link is 100 megabits per second, which matches its link capacity of 100 megabits per second. As a result, each flow receives the full bandwidth, and the observed throughput is 50 megabits per second. Let's discuss the throughput performance of OSPF and RIP. In case 1 with RIP, the 3 flows W1Z1, U1V1, and X1, Y1 achieve a throughput of only 32.70 megabits per second, which is significantly lower than the expected traffic demand. Conversely, in case 2, with OSPF, each flow successfully meets its expected throughput demand. The reason for this difference is that RIP uses hop count as a metric, forcing the X1Y1 flow to use the congested A to B link. On the other hand, OSPF allows flexibility in setting link weights. By assigning a weight of 4 to the X2A link, the X1Y1 traffic is routed through the uncongested X to C, D, E, Y path. As a result, the AB link carries only W1, Z1, and U1, V1 traffic, each getting 50 megabits per second, while the XCDY path provides 50 megabits per second to the X1, Y1 flow. Thank you for watching.